AI Next on the Morning Drive and more. And Nasser Bostan is back. Nasser's the founder of Simulacra X, which is a next generation cognitive cybersecurity platform. Nasser, good to see you.
Hey, Tim, good to see you too.
Where do I find you today? Are you in Cambodia at the moment? Am I right?
I am Cambodia. Just finished some building of some homes, some sort of for underprivileged communities here, some charity work that we were doing, and then should be heading back to the Middle East to Dubai sometime soon.
Oh, okay. Well, we'll catch up when you're here. But good of you to spend some time with us today, Nasser. It's always a pleasure to talk to you. Last time you were here, we were talking about the sapient paradox, and I'll come back to that. But today, to begin with, current AI thinking is that scale is the key. So building bigger chips, bigger data centers, bigger AI models. But you think we're missing the point by doing that.
Yeah, I think we are. We've talked before about how, as you just said, scale is not going to be sustainable moving forward, just because of sheer volumes of data and the amount of data that these AIs need to ingest, and therefore how much compute power that they need. And if you look at history, actually. Exponential intelligence, which is what we're trying to aim for with artificial intelligence, there is actually a deeper pattern that we talked about with the sapient paradox, but also when we talk about how we should be computing things. So there's a couple of concepts that we'll talk about today. One is how compute is actually done, and secondly, how knowledge can be extracted from systems.
So at the moment, we're doing what we always do, aren't we? It's kind of a brute force approach to AI. And one of your contentions is that to fix the issues that we're facing, we need to take more of a physics first approach.
Exactly that, yeah. So let's just start with the first concept, as you said, about how systems compute. So existing systems today, they compute every single operation, the laptop you're using, right up to data centers. Every single operation that's requested is computed, whether it's useful or not. And we deal with the physical consequences afterwards. We need bigger, as you said, bigger microchips. We need huge compute clusters. And of course, these generate heat, air conditioning is required, water cooling, massive power requirements. But I think we need to ask a more fundamental question, and that is, which operations should actually be allowed to even run at all? In other words, how do we consider the physics before we compute rather than dealing with it after we compute? So basically treating information qualities and computation as a physical property governed by the same laws as the physical world.
So we need to be considering sciences. We need to be considering the laws of physics and the laws of thermodynamics in our approach to artificial intelligence.
Correct, exactly that. And there's four main concepts, and I'll just sort of run through what that looks like. So the four concepts are state space evolution. I'll describe what that is in a second.
Right.
As you said, the laws of thermodynamics, something called stability theory, and something called coherence. Let's start with state space evolution. All digital systems, they exist within a state space. That's kind of the full set of possible configurations of data, processes, and network conditions at any given moment in time. And actually, it's all systems full stop, whether they're biological systems or artificial systems. So in the case of computer systems, every single action, as I mentioned, whether it's a packet, a query, a process, or an instruction, it moves the system from one state to another state. And looking at it sort of biologically, if we froze in time the room that you're sat in right now, the arrangement of all of the things and people in that room would represent, the current state space of that room. And if we had the power to press play and then pause it again, the new configuration would be the evolved state space. And we call that state space evolution or transition, moving from one state to another. So if you apply it back to computer systems, at the moment, because the systems are computing everything, the state space transitions don't have any overall coherence or control. It's basically an amalgamation of millions of different actions happening in an uncoordinated manner.
So what other physical laws are we talking about here, Nasser?
Well, the state space evolution leads us directly to the second law of thermodynamics, which is entropy always increases within a closed system.
Right.
As you know, entropy is a measure of disorder or chaos or unpredictability within a system. We know, as we said from the second laws of physics, that within a closed system, entropy will always increase. Chaos and disorder will always increase. For example, if you leave ice cubes out at room temperature, they'll always melt into a disordered puddle of water. That's increasing entropy or increased disorder. The ice cubes will never spontaneously reassemble back into solid ice cubes, right? Entropy is always the other way around. So
Right.
basically, without any outside intervention, entropy is always going to increase. Now, networks obey the same physics. Without any intervention, every system is going to decay into inefficiency, less order, more chaos. For example, your phone, that's why it gets slower and hotter over time. Apps are leaving behind fragments of data, background processes are accumulating, data piles up like digital clutter. Basically, your phone is getting more and more and more disorder within the system. And it's this uncontrolled approach to computation that's directly making all systems drift naturally towards higher entropy. So that's kind of why how entropy comes into it. But then, of course, there's the first law of the thermodynamics, which is the law of energy conservation. Energy is never created or lost; it's only ever transformed. So if you look at computer systems, every single computation consumes energy and generates heat, right? So and you can every physical change or logical change within a system has a physical cost that can be calculated. So in simple terms, if you avoid unnecessary computation and wasted state transitions, you're basically consuming less energy and producing less heat. Turning on your laptop makes it hot because the electric energy used for computing is transformed directly into heat energy. So basically, it's all about transition of energy rather than getting rid of energy, as they said.
Okay, so given the first law of thermodynamics, the second law of thermodynamics, that leads you to what? Stability theory, right? Which is when things return to equilibrium.
That's exactly right. All stable systems return to equilibrium after, that's balance, as you said, after a disturbance, right?
Right.
Unstable systems will sort of oscillate or diverge rather than returning back to a stable equilibrium. For example, if you disturb a glass of water by splashing or creating a wave, because it's contained within a glass, the water will eventually settle back down to sort of flat, motionless state, back to equilibrium. So it's a stable system. And so in simple terms, what we're saying is that small disturbances should not cause uncontrolled runaway behavior. And that's part of the concept that we're talking about here.
Okay, so with you where we are now, the next point is coherence. The measure of whether, am I right here, an incoming instruction, a data request, a software process, or I don't know, network traffic is physically and thermodynamically consistent with the stable operation of the system, and that this is kind of the outcome phase, I guess.
Yeah, you've hit the nail on the head, Tim. So all of the other laws, and there are a couple of other laws that I haven't spoken about, but they're not important for this discussion,
Right.
directly contribute to exactly what you said, which is coherence, right? And so that is a measure for how coherent a signal is, and therefore whether that signal should be allowable to be computed or not. So high coherence signals, it's kind of like a musical note, a perfect musical note. those are essential to the required outcome, i.e., the song that you're trying to play, right? Or in the case of the computer system, the operation that you're trying to execute. And those would be permitted to be executed automatically because the system is now obeying these laws that we talked about earlier. But low coherence signals, which are sort of noise and malformed requests, unnecessary computations, are blocked before they consume any energy or before they destabilize the system. So basically what you're doing is you're getting 100% of the output for a lot less of the actual computation that you needed. So in simplest terms, the system basically asks, does this request make physical sense? And does it contribute to system stability and the evolution of the state space before it decides whether it should execute it?
I'm with you. Okay, so if we're able to ensure stability, coherence, order to all intents and purposes, that's a far more efficient model. So can you break down just how much more efficient it could be?
Yeah, the figures are quite interesting actually, and just to be clear, these are the statistics I'm going to mention are based on mathematical and computational simulations, so are yet to be tested in the
Right.
real world.
Okay.
But the simulations would suggest that with this approach, you would only need to execute around about 15% of the proposed operations rather than the 100% as it is today. That's effectively eliminating 85% of unnecessary work, preserving 100% of the functional output. What would that mean? That would mean that you're looking at an 85% reduction in energy requirements, theoretically no need for any water consumption, and theoretically no need for any air conditioning, and a system that could operate at temperatures from minus 45 degrees centigrade to 85 degrees centigrade. So as you can see, a fundamental change in how we do things today.
I mean, if that could be achieved, Nasser, that would be, well, the only word is huge, really, to paraphrase the US president. But, this is not tested. This, you were at pains to point out, this is a mathematical theory at the moment, really.
Yeah, there is some basic testing that has been done on a very, very small network. So there is a basic version of the software. And just to be clear, this is not Simulacra X technology. This is a partner company that we're working with at the moment who own the technology, have come up with a theory, and are basically now starting to look to move into real world development and testing. Obviously looking for funding to do that. But yes, to answer your question, this is theoretical, tested in a small scenario, but now ready to be deployed and tested at scale.
Okay, so AI is everywhere at the moment, as we know. It's your almost your existence these days, in some ways, I suppose. But where are we? And it's funny because I seem to ask this question a lot. I think about this a lot. How clever is AI right now? I'd like to kind of get to that in this conversation. You've written a paper about resolving the sapient paradox. We talked about that the last time you were on, a month or so ago. But let's recap what the sapient paradox is, why it's important in terms of understanding and thinking and intelligence as well, and also why do we need to resolve the sapient paradox?
Yeah, the sapient paradox is a sort of long-standing puzzle that basically historians and archaeologists, were trying to figure out why the anatomically modern humans who've been around for at least 100,000 years and probably more showed absolutely no civilizational or technological progress until around about 10,000 years ago, at which point we saw an exponential increase in civilizational and technological progress. There's been a number of theories to try and explain it, from environmental factors to the size of the human brain, but nothing that's really kind of landed. And as I mentioned last time, I'm proposing a new resolution that's based on a couple of concepts called knowledge density and cognitive yield.
Okay, so we now need to ask, what is knowledge density and what's cognitive yield, Nasser?
Yeah, so knowledge density is basically, you define it as the degree to which information and insights and models of things and concepts in the world, you can aggregate them and structure them and make them accessible within a system. And that system could be biological, like we are, or artificial. And high knowledge density arises when all of those elements of knowledge are kind of richly kind of interrelated and contextualized, and you understand the relationships between those disparate pieces of information. Cognitive yield is basically the effective analytic output that you can then derive from the high knowledge density that you've got. So that is new insights, discoveries, innovations, everything like that a system can generate from its knowledge base within a given period of time. And what we've seen and calculated is that once you hit a critical mass of knowledge density, you'll see an exponential increase in cognitive yield. The human brain works in exactly the same way. So when you're learning a new subject, say you're at university or something, at first, as you're trying to assimilate the knowledge, it kind of you don't get it. You're still trying to understand it. You're still trying to make all of the connections between those different information points that you're getting. But once you reach that density of knowledge, your brain unlocks its cognitive ability to understand that particular subject and cross-synthesize it with all of the other information and knowledge that you have, right? So we humans demonstrate knowledge density and cognitive yield, on a daily basis, basically.
Okay, so how did that contribute, knowledge density and cognitive yield, to human civilization?
See, for most of prehistory, we were hunter-gatherers. We roamed around in small, dispersed groups. We didn't really have any means of recording or transmitting knowledge across generations. So, and that obviously lasted for most of the time that we, as anatomically modern humans, have existed. However, due to the factors I mentioned earlier, environmental changes, etc., we moved to these agricultural societies. And when we moved to agricultural societies, it was the first time that large numbers of humans came together to cooperate and collaborate, into building these communities. And what that meant was that we were then seeing the emergence of, writing systems, cuneiform, things like that, codified laws, building archives, obviously educational institutions. And all of this meant that we now had accessible stores of knowledge. Now, making that knowledge accessible across both time and geography, i.e. localized knowledge, that meant that we were able to build sort of structured knowledge bases that grew just beyond individual memory. And so the overall knowledge density of civilization increased. And if you look at that throughout history, the agricultural age, the Neolithic revolution, the Enlightenment, the Industrial Revolution, and now the information age, all of those correspond to points in history where we hit thresholds of knowledge density and unlocked these exponential gains in cognitive yield.
Okay, so by your thinking, your belief is that knowledge density and a new compute paradigm are therefore the keys to AGI.
I think so. I mean, if we look at current architectures, as I mentioned earlier, large language models, the people like Yann LeCun, who's one of the sort of fathers of neural networks, he's already, declared, as he's set up his own company at the moment, declared that, the current AI is just not capable of AGI, artificial general intelligence, because of its limitations around the amount of information it needs to centralize and the opaque nature of the way that the system is architected. Now, if we look at the two concepts that we've just talked about, first of all, compute, data is basically unprocessed signals. It's the raw zeros and ones that are contained or housed within systems and are transmitted across networks and utilized by applications to then come out with coherent things. For example, this video right now is turning zeros and ones into the video that we can see, or Word is Microsoft Word, Excel, whatever. These are the applications that turn those on-process signals into applications. So taking the first concept, if we can reduce the amount of actual computation that's required globally to move and process data, that's going to be a fundamental shift to get away from the inevitable fact that data is going to increase exponentially, over the next few decades and years and centuries as we continue to evolve. And then the second piece is, okay, so now let's say we've solved the compute problem, right? We could shift data around and not worry too much about computation. The second problem is, well, how do you structure that, the knowledge that you can extract from that data in a way that achieves the knowledge density and the cognitive yield that you require? And as I said, existing systems don't do that today. So I believe that the way we need to be looking at this is accessing knowledge at source via globally distributed architectures that don't need to centralize massive amounts of information and data.
AI front and center right now, but if scaling isn't the answer, I'm wondering what actually creates artificial general intelligence?
Yeah, great question, Tim. For me, as I mentioned, it's not centralization. That's not the answer. Apart from the fact that it's physically not scalable. I personally believe that having singular entities controlling technologies as powerful as that is not the right thing to do. I think it should be a technology that's more accessible for everybody than under the control of a single entity. We'll probably talk about that more later on. So basically, I believe it'll come from building systems that have got real-time access to evolving knowledge, but through distributed or decentralized systems at global scale. So not moving data centrally, but accessing it at source and extracting only the knowledge that the system needs for whatever use case it's been tasked with. So right now, as we said, AI is like a big warehouse. It's full of books. It's no proper cataloging. It's opaque. And of course, it's inherently probabilistic in its outcome. It'll give you probably the right answer because all it's doing is predicting the next sentence. It doesn't have a semantic understanding of what it knows. But AGI is obviously going to require something different. It's going to need that access to real-time structured knowledge at global scale and the ability to properly reason across different types of domains. So that's all about underlying architecture, not about scale.
Okay, so who's building systems like that, Nasser Bostan?
Well, Simulacra X, we're on the journey, basically. So we are building a system that utilizes what we call knowledge hyperspaces, and I'll explain what that means. So we're kind of focused on the knowledge layer. I mentioned earlier about this partner company that I'm aware of that's starting to look at how data is processed and moved and how you dramatically reduce that. But what I'm focused on is the knowledge layer. So what we're saying is that, okay, instead of training one massive centralized model, we build what we call knowledge hyperspaces. Let me explain what we mean by that. At the practical level, we deploy these software adapters at the source of the data. That could be anything. It could be your phone. It could be a server. It could be a laptop. It could be anything. And these adapters are built to create what we call entities. These are real-time representations of people, systems, devices, places, concepts. And the adapters are designed to basically extract the knowledge or the information that's required from the data source to create this entity representation. The entities, as I said, only extract what they need for their specific intended use case. But crucially, unlike sort of digital twins that you see today, these entities have the ability to reason over their local environment. So unlike LLMs, these entities both extract knowledge and understand and are able to reason over that knowledge. And the entities basically would be able to communicate over a special communication protocol that allows them to exchange knowledge with each other at global scale. And so in that way, what you're doing is you're creating this sort of decentralized but living and constantly updating knowledge hyperspace. It's something doesn't exist in the way a centralized data lake currently exists. It's effectively it's a manifestation. It's an emergent property of all of the interactions going on between all of these entities. So in exactly the same way as human intelligence emerges from the result of interactions between our individual neurons, this is the concept of this is the same. You have this virtualized manifestation of a knowledge hyperspace through the interactions of individual entities.
Okay, so I need to understand, how is it different compared to the current AI models that we're all kind of becoming accustomed to?
So AI models centralize. They create nodes within their system, and these nodes are representations of words or images in a pixel or things like that. And then each of these nodes is programmed with a weight or a bias that tells the system how important or how much that individual concept or word relates to other associated words and images and things like that. So it's able to detect patterns very, very well indeed, and simulate, therefore, what we see today, which is like very coherent ability to communicate and talk, synthesize and information and predict what it believes to be the next word. And you've seen obviously the way it generates videos now and these incredible little movies that they're generating at the moment. But as I said, what it doesn't do is have any form of semantic understanding or true reasoning capability over that. It's literally just pattern matching. And what we're doing in Simulacra X is that we're saying, because the specific pieces of knowledge remain with the individual entities, we can trace the relationships. So rather than it being this opaque sort of centralized, box that you really don't know how it comes out with what it's coming out with, we have the ability to create this living dynamic map of the knowledge and how it's all linked together. And the key thing with it is that because of the nature of the way it's architected, you can connect literally trillions of entities and define quadrillions of relationships between them. There's really no limit there. So theoretically, you could actually model the entire world. Like literally everything in the world could be modeled within the knowledge hyperspace. And so if you think about what AGI would need to do in terms of access to knowledge, you can see that how that new approach to the architecture may solve the problem.
It's kind of mind blown, isn't it? How does it reason, Nasser?
Brilliant question. So the reasoning capability comes from what we call analytic engines, right? Again, what we can't do is try and have a centralized systems of neural networks that try to have access to all the knowledge and therefore try to process everything. Like I said, it just doesn't work. What we're saying is, okay, you have decentralized knowledge that's effectively centralized through interactions of all of these entities. So now that gives you the knowledge density that you need, right? So how do you create the cognitive yield? And what we do is we build analytic engines. These are sort of specialist reasoning agents, and they can be programmed for any use case. For example, we could have an analytic to measure the current state of a network against the latest known cyber threats. We could have another one to detect anomalies within the network, that might indicate, system failure. We could have another one that synthesizes cross-domain relationships, like, I don't know, between biology and chemistry and mathematics, this kind of thing. Whilst we're focusing very much on cybersecurity as our first use case, you can see from what I've just explained that the potential for the architecture is unlimited. You could literally configure any use case that you want in there. Now, the analytics themselves are programmed to be able to understand which entities and other analytics within the knowledge hyperspace they need to execute the task that they require. So think of it rather than, as I said, like rather than one central monolithic thing trying to do everything, you've got this whole ecosystem of analytics working together, accessing the entities for the knowledge that they need to generate the overall cognitive yield that's required to pretty much solve any kind of use case that you want. So you can see from that it fundamentally departs from how we do things today.
So, where, I suppose, does AGI fit into that?
That's such a good question again. So as I mentioned, in the same way that human cognitive yield emerges and increases from this critical mass of knowledge density, if we engineer a system with the underlying architecture that I've just mentioned, we could see AGI not as something that we need to architect, but as or switch on, as it were. But it may emerge naturally in the same way as human cognitive yield emerge naturally from our brains because of knowledge density. So I use the word emerge there. Emergence is actually the key. You're probably aware, Tim, that it's a scientific field that's only kind of relatively recently, within the last couple of decades, begun to be studied. And what do I mean by emergence, right? Emergence is, for example, individual water molecules. They're not wet, right? But when you combine 1.67 to the power of 19, that's 1.67 with 19 zeros after it, together of these molecules, you'll form a drop of water. And the drop of water has the property of wetness. So how does wetness emerge from non-wet subparts? We don't know, right? That's an emergent phenomenon that just seems to occurs without any connection to its individual subparts. And similarly, if you look at a single ant in an ant colony, sorry, it's programmed to perform a very specific function. They have very limited cognition. But if you put enough of them together, you get this emergent collective intelligence that can build a very sophisticated colony, hive, and a societal structure that allows that hive to function as a coherent single entity. That's again emergent intelligence. So my belief is that artificially intelligent systems with the ability to reason will be an emergent phenomenon out of underlying individual subparts.
Okay. So, Nasser, I fed your notes ahead of this interview into two AI models, Copilot and Gemini. No particular reason, they just came to mind, and Copilot immediately pops up when I create a Word document. So no specific reason for that. Now, most of the questions based on the notes were kind of the things that you and I would naturally kind of come up with in most cases, but there were a few things that piqued my interest. So first of all, and this was a Copilot question, and we're back to emergence there, which is a fascinating topic. What does emergence mean for artificial intelligence, and what might it look like?
So I think for me, emergence from artificial intelligence, we've got to take a kind of a step back as to say, sorry, I've lost you on the video for a second, but yeah, we need to. There we go. Sorry.
Still here. We're still with you.
Yeah, we're still here. Okay, AGI. What was the question? Sorry again, Tim. It was.
What does emergence mean for AI? What might it look like?
Yeah, so see, people always envisage AI as some kind of single entity that's going to rule the world, and AGI particularly so. That is not realistic because you cannot possibly have a single entity that can do everything. It's just simply impossible. Secondly, there is no country in the world who's going to agree for some singular entity to, control their their AGI,
No.
right? So I believe that what we're going to see is singular and individual AGIs that may, for example, be relevant to a country or a company or some other entity, but all of them sooner or later will converge upon a common architecture in the same way as the internet enabled, global communication as we see it today. We'll see a underlying architecture, as I mentioned earlier, that will give rise to individual AGIs that will utilize their own knowledge hyperspaces to do whatever it is that they've been tasked to do. The beauty of that approach is, that, of course, we've talked about this before, Tim, about ethics and morals and principles, and how do you cater for the fact that, laws, regulations, ethics, morals, principles differ from society to society and country to country.
Yeah.
And so you can't have a singular monolithic AGI because that doesn't factor in these nuances and these differences. So if you have your own AGIs that factor those laws and principles and morals into it, but also have the ability to collaborate and cooperate, because these individual hyperspaces can be linked together to allow that cooperation and collaboration, not just across countries and companies, but across disciplines. For example, if we're looking at, say, cancer research, and we think there's a link between cancer research and neuroscience, then, those hyperspaces could be brought together into a single collaboration. So I think that, for the good of humanity and the forward momentum of us as a species, that we should not be thinking about singular AGIs. We should be thinking about individual intelligences that can collaborate and cooperate with each other.
Also, on the topic of emergence, Nasser, your example was a comparison of AGI to the wetness of water. This was a Gemini question. If we don't understand how it emerges, how do we keep control of it?
Yeah, good question again. Control is so control and privacy. Those are two fundamental parts of this, right? So let's talk about privacy, and then we'll talk about control. So privacy today, we know that most of us don't have it, right? Our data is used by many different companies and governments for all sorts of purposes, most of which we don't give our permission for. And so what utilizing a distributed architecture with these adapters and entity enables is that you can deploy privacy at source, i.e. the adapter and therefore the resulting entity is only able to access the information that A, is legally allowed to, or B, you want it to access. Right, so that allows you to bake in privacy at source, and it's a fundamental part of the architecture. Is how do you make sure that privacy is guaranteed? And then in terms of control, this is such an interesting question because, again, going back to what I was saying earlier, control is going to be down to individual people, individual companies, individual governments, individual communities, however you want to define it, because you cannot have an AGI that's going to be controlled by one entity. You have to have something that is an intelligence that's accessible by everybody, but not controlled by nobody. And that's what I believe AGI needs to be, and how we need to architect it.
Both of the AI, the LLMs I use, Copilot and Gemini, asked about risk, asked about who's in charge. Gemini asked about the ant colony model. If AGI is an ecosystem rather than a single brain, who or what is actually in charge? And then Copilot asked, what's the single biggest risk in building systems like this? Natural questions that, we're all wondering about.
Yeah. For me, the single biggest risk of building systems like this is the risk that somebody takes control of the overall architecture. Now, I would hope that that's going to be very difficult, only because it's like somebody taking control of the entire internet. Right? I mean, you can't do it. You can certainly control it within individual geographical boundaries, like we've seen in certain cases recently. But there's nobody with the button to control the entire internet all over the world, and that's one of the beauties of why the internet was so revolutionary. And I think this is the same case with AGI over a distributed architecture, is because it combats the ability for a single entity, country, whatever, to assume control over everybody else.
It's the remarkable thing about the internet, isn't it? That we have this kind of wildly disparate, decentralized system that has become so central to our lives. It's one of life's amazing ironies, I think. Nasser, I thought this was a really interesting question. And again, this is a Gemini question. I can't claim credit for any of these towards the end of this interview. But I thought this was something that you would have a unique perspective on. Is intelligence a slow climb, or does a sudden light switch kind of flip once you hit that specific knowledge density?
It's a slow climb at first, but once we hit that critical mass, we're going to unlock an exponential increase in analytic and cognitive yield of the system. And that, for me, is, if we go back to the whole risk question, that for me is the critical point where, all these discussions we've had around whether AGI is going to be beneficial or it's going to kill us all, that's where that question really comes into play. Because at that moment of critical mass density and the unlocking of exponential analytic yield by a future AGI, we may not know what it could be capable of. And I think that's where we need to be able to architect the boundaries within what that AGI is capable of as early as possible. And also goes right back to what I was saying about the beauty of a distributed system, is that an AGI going rogue or an AGI being beneficial is all going to be down to what it can access and how it utilizes the access to that knowledge. Now, if you've decentralized all of your knowledge, it means that theoretically you can switch off access to that knowledge as well. And you can only give access to the bits of knowledge that you want your AGI to do. So as I said, if you weigh up the decentralized nature of the architecture versus the risks of centralizing it all into one monolithic AGI, then it's far, far less risky, and I think is much more of a viable way of us surviving AGI.
Two more questions for you. The first is an AI-generated question again, which fits, I think, here. I think it's a reasonable way to do it. And then I'll ask you a very human question, maybe to finish off, Nasser. But this was Gemini again. Also asking for a comment on the bottom line, your contention that, scale perhaps isn't the key. So this mathematical theory that you are now testing, are you ready to plug this in and prove it tomorrow, Gemini asks?
The compute part of it is ready for a small scale test,
right?
But that's going to need some investment. So, which I won't go into that. For Simulacra's knowledge system, we have most of the underlying plumbing ready. Which is, the sort of server network, the communication protocol, the standard design of the adapters, what entities will look like and how we'll build them. So now what we're doing is we're spending the foreseeable future building the first use case, which is the cybersecurity one. And I deliberately chose cybersecurity first because, we've talked about risks, right? So if we build the system as a cybersecurity proof system in the first place, That means any other use cases that we build in the future will have all of that learning already baked into it. And so we're kind of trying to build safety into it right from the beginning. So to answer the question directly, the compute thing is ready for small scale testing, and I'd say is probably a year away from moving beyond that. Simulacra X, we are right slap bang in the middle of developing the cyber use case. So I would hope that the world will see a decentralized knowledge hyperspace some point soon.
Final question for you. So essentially, you're saying that artificial general intelligence is a phase transition, a little bit like the industrial age.
That's exactly what it is. We will hit a point, if we architect this correctly, we will hit a point where we will hit a sufficient amount of knowledge density to unlock the next phase transition in human evolution. And I believe that the distributed way that we want to architect it is going to be the underlying architecture that will allow us to do that. So yes, I believe that we are not far off the next phase transition of human progress.
Nasser Bostan is the founder of Simulacra X. It's a next generation cognitive cybersecurity platform. A long background in cybersecurity as well, Nasser. I know that. It's always a pleasure to talk to you. I am off for a lie down now, but in the meantime, I'm looking forward to talking to you again soon. Thanks for joining us.
Thanks, Tim. Always great to speak to you. Cheers.
Good to have you with us. It's Mirror Business FM. This is The Morning Drive.